Hello, Professor. I am Priyatham Chadalawada. My research paper for the presentation is about phantom LiDAR, cross-modality signal injection attacks against LiDAR. So, what is LiDAR? LiDAR is light detection and ranging. LiDAR is a cornerstone technology for autonomous vehicles, providing precise 3D spatial data, which is critical for safe navigation and to map surroundings and detect obstacles. So, here is the image to understand how the LiDAR works. The top one is a real scene. So, as the name itself says that it works on light, which is a laser light emitted from the emitter as a pulse and received it through the receiver and then amplified and sent it to the main board for processing and thus creates a point cloud scene output. The phantom LiDAR research focuses on novel cross-modality attack using intentional electromagnetic interference to disrupt LiDAR functionality. Unlike conventional laser-based attacks that manipulate LiDAR through direct light signals, IEMI targets the internal electronic circuits such as the laser receiving circuit and monitoring sensors, exploiting their susceptibility to electronic magnetic signals. So, here the objective of this study is to expose these vulnerabilities and propose the phantom LiDAR attack framework, which demonstrates severe manipulation of LiDAR outputs from distorting data to shutting down the system entirely. Coming to the problem statement that why LiDAR security matters, LiDAR is integral to autonomous vehicle perception. A LiDAR's role in autonomous vehicles makes its security a critical concern as any kind of compromise could lead to missed obstacles or navigation errors posing significant safety risks. While previous attacks on LiDAR, mainly laser-based, have shown some success, but they're limited by the need for precise aiming, restricted age, and impact on only small portions of the point cloud, making them less practical in dynamic real-world scenarios. And in this research paperwork, they have also noted that previous electromagnetic interference attacks only caused minor data perturbations insufficient to disrupt LiDAR's core functionality. So, because of this, this leaves a critical research gap that is, can IEMI exploit new attack within LiDAR systems to achieve more severe and practical effects? As discussed in the research paper, there are limitations of laser methods, such as their 35-degree field of impact, high aiming requirements, contrasted with the potential of electromagnetic attacks to affect a full 360-degree range. Now let's see an overview about the phantom LiDAR attack. Despite electromagnetic compatibility testing, LiDAR's internal modules, specifically the laser receiving circuit, mounting sensors like temperature and Hall effect sensors, and the optical encoder in the beam steering module are very vulnerable to intentional electromagnetic interference. I'm going to explain about the components that are critical to LiDAR's operation and the IEMI signals leading to malfunctions. The attack surfaces include the receiving circuit, which affects the time of flight, ranging accuracy, mounting sensors, which trigger fault detection mechanisms, and the optional encoder, which can halt beam steering and shut down the system. And for this one, the methodology involves using high performance electromagnetic devices such as RF antennas and signal generators to inject tailored signals that either directly disrupt ranging or directly exploit the LiDAR's fault detection and diagnostic mechanism, forcing it to error states. The Phantom LiDAR introduces four distinct attack types, each exploiting the identified vulnerabilities to achieve significant disruption. The first one is the point interference. If you look at the right side picture, there's a sinusoidal wave in a green color in the middle one. So that's the interference signal that can be injected into the receiving circuit by EMI, causing minor variations in the peak time of the return signal. This subsequently causes a slight shift in the position of the points, either forwards or backwards. This distance shift is defined as distance error, which can quantify the intensity of point interference. Right side, if you see the two pictures, Um, the top one is the original points, and the below is the interfered points. This points interference injects errors up to 10 centimeters in LiDAR ranging, distorting point clouds and degrading perception accuracy. And coming to the second type, which is the points removal, it displaces or completely erases point clouds, effectively hiding objects from detection models. Okay, this is a critical threat in autonomous driving. So here the third one is LiDAR power off, which shuts down the entire system by targeting the beam steering module, requiring a manual reboot to restore functionality even after the attack ceases. When connected to LiDAR power off attack, the rotation speed of VLP-16 LiDAR significantly decreases from 600 RPM to 19 RPM, then leading to denial of service and ultimately resulting in powering off. Coming to the fourth one, which is the points injection. If looked into the flow chart, the efficient EM injection module identifies the optional conditions for a carrier signal and transmission, which then combined can achieve the maximum intensity of electromagnetic injection. The effective point injection module models the LiDAR parameters and design baseband signal that can inject points. The point control module introduces a closed loop feedback mechanism integrating receive and delay control. The points injection uses amplitude modulated electromagnetic signals to insert over 16,000 controllable fake points, such as pedestrian pattern, to deceive detection systems. These points removal, power off, and injection are entirely new attack types, and the interference attacks is twice as potent as prior methods. To validate phantom LiDAR's effectiveness, the researchers tested it on five commercial off-the-shelf LiDAR systems, including three rotating models like the VLP-16 and two MEMS-based models like the RS-M1, ensuring broad applicability across common LiDAR types. The picture shows an experimental setup which used affordable attack devices such as RF antenna, signal generator, and power amplifiers. The experiment covered both static and moving scenarios, achieving a 83.5% success rate at 5 meters, and while static, 87.2 success rate at 4 meters. The results of the phantom LiDAR experiments demonstrates its alarming effectiveness and real-world threat. For points injection, that attack injected over 16,500 fake points into the VLP-16 LiDAR, which is 5 times more than 3,000 points achieved by state-of-the-art laser-based attacks, creating deceptive structures like a circular wall around the LiDAR. The points removal successfully hit targeted objects without requiring precise aiming, which is a significant advantage over laser methods. The power of attack disabled LiDAR systems, which with effects persisting until manual reboot, posing a severe denial of service risk. These attacks reduce the average precision of five 3D objects models such as point pillar and PVRCNN, indicating degraded performance in real-world perception tasks. Comparison with laser-based attacks. EM attacks cover a full 360-degree horizontal range, requiring minimal aiming precision, unlike laser attacks, which are limited to 35-degree field and demand exact targeting. In points injection, electromagnetic methods achieve 5 times more fake points, which is 16,500 versus 3,000 in the VLP-16 due to the ability to affect the entire LiDAR circuit simultaneously. And also in cost wise, electromagnet setup ranges from $168 to $2,300, comparable to or cheaper than laser setups, making them more accessible to attackers. These factors make electromagnetic attacks stealthier and more feasible in dynamic scenarios such as attacking a moving vehicle at a traffic light or during tailgating. In conclusion, Phantom LiDAR unveils critical vulnerabilities in LiDAR systems, including novel IEMI-based attacks that manipulate point clouds, hide objects, and even shut down entire systems as summarized in this slide. The attacks outperform laser-based methods in scale, injecting 5 times more fake points and practically requiring less aiming and working in dynamic scenarios. The severity of effects, such as creating fake pedestrians or disabling LiDAR, poses significant risks to autonomous vehicle safety, making this a wake-up call for the industry. Manufacturers must provide LiDAR security by adopting enhanced defenses like sensor fusion and circuit shielding to protect against these threats. Thank you. These are the references I have used. So this is the research paper references that I put in here, and there's a video demo of how this experiment got implemented in practical scenario. And thank you for listening to my presentation. Thank you.